Yes, thank you very much. Good morning. I'm very happy to see so many people here at this early hour. I think I didn't give a talk at 9 in the morning for a long time. Yeah, thank you very much for inviting me. My name is Krenn. I'm research group leader at the Max Planck Institute for the Science of Light. And our research is in the direction of how we can get new ideas from computers, very generally. And that is also what I want to talk to you today. I will talk about how we can get new ideas from AI from two different directions. The first direction is how we can design new quantum experiments and get ideas out of that. And the second direction is how we can use a large amount of scientific literature to also get potentially personalized new ideas. And in the end, I will give you a slightly big picture of what we think can be done in the future. Okay, so let's start. The first part that I want to talk about is how we can design new quantum experiments with computers. And this question came up during my PhD a few years ago. I was in the experimental quantum optics group, in the group of Anton Zeilinger in Vienna, and we wanted to design, investigate high-dimensional multi-particle entanglement, so very complex entangled systems. And so to give you an idea what this means, if we have the simplest type of entanglement is two-dimensional two-particle entanglement. So here, for instance, we can imagine we have two photons where both photons are either red or both photons are green. And before you measure the photon, they don't have a well-defined color. Only when you measure them, the photon gets one of the colors, either red or green, and then its partner photon also gets that color. And this state has been experimentally investigated since roughly the mid-70s. So it's very well understood how to produce and analyze such type of entanglement. But now you can increase the complexity of entanglement. For instance, you can have more particles. In this case, this would be a three-particle entangled system, where all three particles are either red or all three particles are green. And again, before you measure, the particles, they don't have a well-defined color. Only when you measure one of them, all of its partner photons also get the same color. And that is called a GRZ state. And it's quite important when it comes to quantum computers. So to scale up the number of particles in entanglement is very important for quantum computers. And these states have been investigated in many different platforms, roughly since the late 1990s or early 2000s. Another way to increase the complexity of entanglement is not to add more numbers, but to add more colors. So now you can have, again, two particles, where both particles are either red or green or blue. So this is called high-dimensional entanglement. And this is very much investigated in the connection of quantum communication, because you can communicate more than one bit of information per photon that you transmit. And these states are also investigated for roughly 20 years in different laboratories. So what we wanted to do is to investigate complex entanglement that have more than two particles entangled in more than 2 dimensions. So for instance here, 3 particles that are either red or green or blue. And such a state has never been created before at this time. And also theoretically, there were a lot of questions about this type of entanglement. And theorists have found that it has some very peculiar properties that other type of entanglements cannot have. And therefore, we wanted to observe these states and its properties. But of course, the first thing that you need to do when you want to observe the property of something is to create the thing. So the first thing we needed to do is to find the experimental setup that can create such a entangled state. Now, usually that works when we want to create a experimental setup for a new experiment. It works in the following way. We sit down, we use our intuition, and we write down different combinations, and very quickly we find the experimental configuration that works and can produce the thing that we want. So that is basically how it is done in this specific field for the last 25 years. But this approach, surprisingly, didn't work for this quantum state. That means my colleagues, which were, I think, 3 or 4 experimentalists, 2 theorists, we tried to come up with an experimental setup that we could build in the lab for many weeks. And we completely failed, didn't work, never has happened before. After a few weeks, we were really desperate because we knew, okay, it's very interesting and there's a large research area that lies ahead of us if we can start to create such things. So after some time, I thought, okay, maybe we should do something different. We should not use our intuition to create experimental setups, but maybe a computer can help, because a computer doesn't have intuition, so maybe it doesn't have some certain preconceptions that we have, and it can just design on its own without any preconceptions, basically. So, and then I wrote a computer program, actually a very simple one, and yeah, let me explain the program that I wrote, basically. So the idea was that we start with a toolbox that contains all experimental components that we have in our laboratory. So that could be lasers, beam splitters, nonlinear materials, phase shifters, detectors, and so on. And then the algorithm takes those elements and in the first iterations randomly shuffles them at the virtual table. And when after it randomly shuffles them, it makes a few sanity checks. If those sanity checks are okay, for instance, whether there are photons going to the detector, because otherwise it's probably not a useful setup. So if those sanity checks are okay, then it computes the resulting quantum state. And if the resulting quantum state is the thing that we wanted, of course, we are very happy, and it reports to the user. And furthermore, it then simplifies the setup and adds the setup to its own toolbox. And when it adds the setup to its own toolbox, the toolbox increases. And the toolbox has already more complex elements in that it can use in further runs. So when the computer finds solutions for simpler problems and it stores the solutions here, then it can use later to build up more complex setups, can already use those simplified experiments. And so that is a very simple algorithm. And I wrote it, and then I ran it in the evening. And in the morning, I really found a file on my desktop, solution.txt. And that file contained really the blueprint of the setup that we were searching for weeks and for months. So that, you can imagine, was a very good day. And it turned out that this blueprint actually really works. So you can compute it, it works. And actually it was then used as the blueprint that was then built in a multi-year project in the laboratory. So that very simple algorithm was able to come up with a setup that can produce something that we humans were not able to do. And it was useful because we were then able to observe those properties in this complex high-dimensional multi-particle entangled space. So we were, of course, very, very happy about this algorithm and tried to apply it to other questions that we were not able to solve before. And we also found setups for many different applications. For instance, some certain high-dimensional gates that were not known before, some certain type of new measurements that were not known how to perform them before, and so on. And very recently, we also applied actually this basically the same algorithm to a superconducting quantum computer. Namely, we wanted to create exactly the same state. We also wanted to create a three-dimensional free particle entangled state. And that was possible because IBM was exploring high-dimensional spaces. So they were usually working with the level 0 and 1, but they are exploring the second level, so the next higher level. And there were some test circuits, and we were getting access to those test circuits. And it was not clear which transformations one has to do. And I just ran basically exactly the same algorithm. It came up with a circuit. We run the circuit, and we created thereby the first high-dimensional multi-particle entangled state in a superconducting machine. Yeah. So we were, of course, very happy about this algorithm because it is now basically a tool for us to come up with new experiments. But for me, the much more interesting thing was that you not only get new experiments, but you can actually get new ideas out of this machine. Because when you try to solve something yourself for many weeks and you're not able to solve it, and then you see the solution, you see what you have missed, and you can try to understand what you have missed, what the computer did that you were not able to do. And that happened in several cases over the last years. So in one specific case, let me tell you this story. I like it a lot. So after we found this high-dimensional multi-particle G at Z state, I copied this program to some of the unused computers in our lab and let it search for more complex entangled systems. And when I ran this, I thought that there needs to be an upper limit to the entanglement that it can create, because I know that I give it some resources, and with these resources, I was sure that it cannot go beyond some certain upper limit of complexity of entanglement. And sure enough, when I came back a few weeks later, there were solutions that overcame my this upper limit that I thought needs to be there. And so I was very confused. I thought the program has a bug, but actually the solution worked. So it kind of needs to have some idea inside that I didn't understand, because I was sure my upper limit has to work, and the computer overcame it. So then I was looking at the output of the program. The output was kind of complex, and so I looked at it for days and for weeks. And actually then at some point I understood what the computer was doing. It was using completely implicitly an idea that was invented by experimental quantum physicist in Rochester in the US, and then has basically forgotten. So it used the idea to produce some indistinguishability between photons. Completely implicitly, because that was not part of the toolbox, but it used it in a very specific way. If you unfold the setup, then you get exactly the setup that was investigated in the early 90s by this quantum physicist in New York. And as soon as I understood what the computer was doing, I was immediately able to generalize this to many other systems. And maybe let me explain this on this simpler example. So here, this gray box is a two photon source. So this thing can emit 2 photons. This thing can also emit 2 photons. This thing can emit 2 photons, and this can emit 2 photons. And let's say we have the photons are in some certain modes, and all of those photons are created in a mode 0, but you can shift the mode. Okay, so for the experts here, I'm talking about the spatial modes of the photons. For the non-experts, just think about it as numbers. So now we can shift the modes, and I'm shifting the mode with this red lines. Okay, so here, when this crystal produces 2 photons, when they come to the detectors, they are 0. Both are 0 because they are not shifted. This produces 0, but they are shifted by +1 here and +1 here. So if they go to the detector, they produce the state 1, 1. If this crystal produces 2 photons, they are shifted once and twice. So they produce 2, 2. And this one is shifted once, twice, 3 times. So this produces 3, 3. So when we now when we now pump all of those crystals together and they are producing photons probabilistically, one of them produces a photon. You can do it in such a way that that this production process is in a coherent superposition. So what we get in the end is a coherent superposition of those 4 terms. And that is a 4-dimensional entangled state. So what this is a completely scalable 4-dimensional entangled quantum setup. And this idea has never been thought about by physicists. This idea only came out from my understanding of the solution of what the computer has done. And actually, the computer came up with much more complex structures because it can create somehow something like the same tricks, but also for many particles. And we were super happy, and we wrote this down, and we were lucky enough to get this accepted in PRL. And the funny thing is, the main intellectual contribution, which is the idea to do this overlapping and the shifting in a very specific way, didn't come from a human. So the main idea of this PRL paper didn't come from any of the authors of this PRL paper, but it came from the computer. So that is pretty cool somehow. Unfortunately, we didn't dare to add the computer to the author list. That would have been fun. But we added it to the acknowledgement. We thanked it for analyzing 100 million of setups. Okay, so this was the idea that where we understood something from the solutions of the computer. And we then later found that what the computer actually did and why this worked so well was to discover or uncover a link between quantum experiments and graph theory. And as soon as we understood this, you can translate questions of experimental quantum optics to graph theory, solve the questions there with the tools that mathematicians have developed, and then translate the answers back to quantum physics. And we have done this in several ways. For instance, when you go to graph theory, you know that there's a lot of computational complexity analysis there. So we learned immediately some ideas about the computational complexity of some of those experiments, which have connections to quantum computers then. Okay, and some of those setups have been implemented for the first time rather recently. Okay, so one of the problems here with this algorithm was that when you get a solution, it is usually very, very complex. And it's very difficult to understand how and why the solution works. So recently, which means maybe 1 year ago, we came up with a new algorithm. And this new algorithm used exactly this abstract graph representation that we found through the computer, through this earlier algorithm that I explained to you. So we use now this insight that we got from the computer to develop a new algorithm that is way, way faster and more understandable. So what we do is we know now that everything that you can do in an experimental laboratory, in a photonic quantum optics lab within some constraints, you can translate to graph theory, namely to colored weighted graphs. That means edges have colors and weights. And so description here, the vertices stand for basically the path of a photon, and the edge means that the photons in those two paths have a correlation. And the weights here stand for basically the amplitude of this correlation. So now the most general thing that we can build in the laboratory is described by a complete graph where each of the edge has a weight. And now instead of solving a very complicated discrete question that we had to solve before, we can now translate this discrete question. The discrete question is, how do I put my building blocks at the experimental setup? Instead of that, we can now use this parameterized graph and solve the question there, because this corresponds to experimental setup, but also it directly encodes the quantum state. So all properties that you can derive from a quantum state, you can now write down as the weights of this graph. So for instance, if you want to create a certain quantum state, your objective function would now be the fidelity, which is a function of the weights of this graph. So now the algorithm works in two steps. The first step is we optimize the parameters of this graph to minimize the loss, for instance, to maximize the fidelity. And then when we have a configuration of all of the edges, we try to remove as many edges as possible and rerun this optimization and try to get out the conceptual course of the solution from the graph, such that in the end, we get a very small graph. And those small graphs, you can actually basically look at it and immediately understand what they are doing. So that means now we have a tool, we give a question, it solves the question, but it gives you the answer in a way that you look at it and you basically know why it works. So that was a large improvement from before, where I had to sit for weeks and try to think what what is going on. Okay, I maybe give one example, but I think I will only give it very high level. So one important thing is that in photonic quantum optics, it's difficult to produce certain quantum states deterministically. So let's say I want a state now is basically very, very difficult. So what people do is try to build the next best thing that you don't know when the state was created, but if it was created, you get a signal from somewhere else that tells you, okay, the state was created now. That is called heralded entanglement. And it's very difficult to come up with such heralded entanglement sources. And basically, they are the building blocks for photonic quantum computing. For instance, if you know the company PsiQuantum, they use something related to heralded entanglement to build up the resource state for their quantum computers. And a lot of questions are open about this. So we wanted to create a three-dimensional heralded entangled state because that was not known before. So I ran the algorithm. I got a solution rather quickly. Solution looked like this. And basically within a few minutes, I understood why this solution works. I will not go into detail, just the idea is that it creates somehow some fancy destructive interference between vacuum contributions. So it basically has destructive interference between vacuum, and therefore you always get the state that you want. So, and this is an idea that was never described to the best of our knowledge in the literature, that you can use something like destructive interference of vacuum. And as soon as I understood what it is doing, I was immediately able to generalize this idea to many other cases. So in a way, I was able to get some understanding from the machine, and I showed that I understood something by generalizing this to other cases without the computer anymore. So these have been created by me by hand, just by understanding what this guy is doing. Okay, so with this, I would like to close the first part. If there are questions here, we could take the questions now. There's a question soon? Okay. Could you please give us an intuition why a human could not come up with such an experimental design? We were wondering about this question for quite some time. The first setup that we got out looked in a way very asymmetric. So usually when we build up something, it's quite symmetric. And also the quantum state that we were searching for was very, very symmetric. So why would you use asymmetry? And also when you go away from symmetry, there's so much room that you can play. It's very unclear what you have to do. And for a computer, it just didn't matter. So for us, it was probably that we had a hard time understanding asymmetry, which in general is very, very limiting, because probably most of the interesting things come from situations that are not trivially symmetric. I think I cannot say more about this. This is our working answer for now. Mm-hmm.
I'm wondering regarding the algorithm that you're using to search for these configurations, is it just like a brute force algorithm which tries a lot of things, or does it have like a learning or feedback component?
Yeah, the first iterations, it has no insight, it is brute force. But you can formulate the question in such a way that you not only search for one thing, but you generalize your question a bit. For instance, I not only search for the state 0, 0, 0 plus 1, 1, 1 plus 2, 2, 2, but I search for states that have a Schmidt rank between all of the components that are non-trivial. Mm-hmm. And there are much more solutions. Many of them are not the thing that you want in the end, but when you search for that, it already has to create something that is non-trivial. So the setups that it finds there, so it finds setups for simpler cases, but it stores them then in its toolbox. And in the next iteration, you can use them. So as soon as it finds simpler cases, it is much faster to investigate the more complex system. So it has a learning component. We tested it on some very simple cases. It got a speed up immediately of a factor of 10, even for very, very simple cases.
Nice.
Regarding the toolbox, actually, is the algorithm able to like get rid of designs that came up like in first place, but find a better solution to do it better or easier, or to what so how do you put like lab constraints into this? So do you put like constraints like, yeah, okay, we cannot have like 1,000 mirrors or something like that, and
yeah.
it's not possible or whatever.
Mm-hmm.
And then maybe during the training it gets rid of some more or less non-realistic ideas that might work in principle but not in the lab.
So right now we are not using this algorithm anymore because this significantly outperforms it in every metric. It's faster, it's understandable, it gets simpler solutions. Before we were playing with this a little bit, what I added is the possibility to remove stuff from the toolbox. And they are already tried to try to have some weight of when it should delete it. For instance, when it uses it more often, it should not delete it. So that goes into this direction. But we didn't follow up with it because we then later came up with this very different type of discovery engine.
I actually also have a question.
Mm-hmm.
Did you also try evolutionary algorithms or reinforcement learning? And do you have an intuition whether they would work better or worse?
We tried a little bit, and there was at a very similar time when we came up with this first algorithm, other person in the UK, I forgot at which university, Paul Knott, he came also up with an algorithm to design experiments. He didn't look at entanglement, but quantum metrology, and he used evolutionary algorithms. We then didn't compare. I tried to apply evolutionary algorithm a little bit, but at some time we gave up because we were able to solve so many questions with the first algorithm. And if we cannot solve it with the first algorithm, we were also not able to solve it with evolutionary algorithm. So at some point, we just didn't follow up on that. So it could be that it outperforms, but we didn't do, but not for the cases that we were interested in.
A bit the same question, but for reinforcement learning. So I think.
Can you say again?
So for reinforcement learning, did you also compare a bit with what people are doing?
So we did then research after we published this. There was a researcher in Innsbruck, Hans Priegel. He was very excited about this, and he works on reinforcement learning, and we then combined these techniques. It has some, so it is not necessarily faster in the discovery, but it can do something else. It can simplify or find simpler setups automatically. It's not completely clear why that was the case, but it found simpler setups than our algorithm. We had to write a handwritten simplification algorithm, while that was not necessary for the reinforcement learning. But for discovery itself, it didn't outperform. And it cannot outperform this algorithm. Because if you think about what a reinforcement learning algorithm is doing, it is learning a strategy to solve a task. But if you can formulate the problem itself as a task that you can solve with gradients, you directly solve the correct problem, and you don't need to indirectly solve it via a strategy. So I think in most of the cases, when you have your problem in a parameterized way, it's easier to solve it directly than with gradient descent. That might not always be the case. For instance, I know in quantum circuit designs, there are some questions because their gradients not necessarily help when the circuits get larger because of some problems that are called barren plateau. But in all of our cases, that was the case. Okay, then let me come to the second part, and I think I will be very quick with that. So if we go back to the original question, or ask the question more generally, we have the goal to have a computer program that gives us interesting and surprising ideas. So now we need to know, what does it mean to be surprising or interesting? And this is obviously very subjective and depends very much on our previous knowledge. So now the question is, how can we get this previous knowledge into the computer such that the computer can actually work with it? And I was very much inspired by a work that was done in computational sociology and computational biology, there people actually have shown how you can build up knowledge networks from large amount of scientific data in a kind of simple way. So what they have shown and what I have then used in quantum physics is that you can build up those knowledge networks where the vertices of the network are concepts and the edges are drawn when two concepts are investigated together in a scientific paper. And this very simple knowledge network actually contains a lot of information, a lot of useful information that has been shown by these computational sociologists and biologists. And I wanted to basically also try that, to build up a knowledge network, actually an evolving knowledge network, if you think about it, because the vertices are the concept and the edges are drawn when concepts are investigated together. But this is a timestamp. That means you see basically the evolution of what is investigated in quantum mechanics, for instance, if you have such a knowledge network. And so the important thing is we need now a lot of data, a lot of scientific literature, and we need the concept list. The concept list are created using Wikipedia and quantum mechanics book and natural language processing from papers from arXiv. And these concepts were roughly 6,000 concepts. They were the core, or they were the vertices of my network. And then this co-appearance, for that I used all papers that have ever been published by the American Physical Society. So that was kind of cool. I knew I need all of these papers. And so I wrote an email to APS and asked them, hey, can you please send me all of the papers that you have ever published in the last 100 years? And one day later, I actually got the Dropbox link and they said, sure, here it is. That was really cool. They sent me, I think, 750,000 papers. They didn't send me the full papers, but they sent me the metadata that contained title and abstract, and I was fine to work just with title and abstract. So now, with that, I was able to build up a network that evolved over the last 100 years from concepts of quantum mechanics. And okay, when you have the evolution, obviously you can think about predicting what will happen in the next years. So for instance, you could think about asking a question, which concept that have never been investigated before will be investigated in the next 5 years? And this, of course, could be solved with a neural network. And what we have done here, or what you can think about, you have your semantic network or your knowledge network, for instance, from 2017, you give this information into the neural network, and the neural network, for each unconnected vertex pair, so for each concept that is not investigated by scientists yet, it should predict whether it will be connected, yes or no. And now I have this knowledge network for 2022. So I can give a simple supervised supervision signal. And then as soon as the neural network learns how to predict this, I can immediately use the data from today and predict what will happen until the year 2027. So 5 years into the future. And actually we have seen that the quality is surprisingly good. And so that is a thing that I investigated 2 or 3 years ago. And last year we did the same for the field of artificial intelligence, because there it is known that research just grows exponentially. So the number of scientific paper grows exponentially. So basically, as a human, you cannot read everything in your field anymore. So you need to focus on a small subset. And we have seen that you can get extremely good predictions with that. Actually, I have done an AI competition with a prize money of 25,000 euro, and there were 40 teams that participated, and we saw that the prediction quality is incredibly good. That means you can get very high prediction of what will happen in the next 3 or 5 years. And you could now think about using this as personalized suggestion. For instance, I take only concept that I'm interested in and look for concepts that are not connected, look for connections that are not connected yet, and see what might be connected, what might be interesting to connect. So for that, it might be useful in the future to have something like a metric of success, which means, for instance, where I can also predict somehow citation rates. So imagine a tool where you give all of your papers and the tool suggests you, okay, try to research, try to find the research connection to this field because it has never been done, but I predict it will be highly cited if you succeed. So that would be a really cool tool. I'm not sure whether that should be online then, what will happen, but okay. Okay, let me come to my second to last slide. I want to show this in a slightly bigger picture. So recently we wrote an article that was just accepted in Nature Review Physics on how we can, in general, get understanding from AI. And one of the core classes that we basically wrote down was that AI can be, as I described, kind of a source or resource even for inspiration. And there are a few different possibilities. For instance, one very much investigated one is anomaly detection. So if you find anomalies in your data in a very non-obvious way, it is usually a very interesting thing. For instance, the entanglement structure that I found was basically an anomaly. I expected that there should be a boundary, but that there should be a threshold, but it found a solution that is far outside of the thing that I expected. So as soon as you find anomalies, you can investigate them and try to understand where they come from. Different example is using the scientific literature. Use a lot of scientific literature. I give one example. There are several other cool examples in material science and chemistry where they used large amount of scientific literature and try to predict properties of elements that have never been measured before, and so on. A different method is interpretable results. For instance, my example with the graphs, here I get interpretable results and I immediately can understand how they work. There's also a lot of work in trying to get out formulas directly from neural networks instead of getting a very complicated output. You could get out formulas. Different method is interpretable or trying to interpret what the neural network is doing. And we will hear in a few minutes a talk by Sebastian about exactly that. He's interpreting in a way what and how the neural network works. So basically he's forcing it in such a way that that we can later understand what it has used to solve the question. And the last part, which as far as I know is not used at all in any field of science yet, is trying to observe the behavior of a machine when it explores a large space. So imagine you have a machine that wants to explore a large space and wants to find the best quantum experiment or something. But now imagine you don't give it an external reward. You don't give it an external reward and say, this is a good quantum experiment, but its reward is an internal reward, namely the quality of how good it can predict its next step. So you would need now a program that not only explores, but also can predict what its exploration steps will do. And this is basically called curiosity-driven exploration. That is in the field of computer science that is much investigated, but nearly not in the natural sciences. And then when you have only this intrinsic reward, the machine will explore the space and enter places which it finds difficult to learn or to predict. It will stay for quite some moments. And those are probably very interesting places, because if the machine has a problem with predicting what happens in these places, probably there's something different from what it has seen before. And then one could look at those places and see what is going on there. Yeah, that would be really cool, observing the machine's behavior. Okay, and with that, just very quickly, we have now this very efficient algorithms to design new experiments, and we can also get new ideas and concepts out of this algorithm. One can also think about predicting the future, some part of the future of research, and this could go towards personalized predictions and suggestion what you should do. And yeah, I'm working on this, and at some point I'm really worried whether this should be open source tools or how one can use this in a safe way, such that this tool doesn't do some crazy things like producing self-fulfilling prophecies. If too many people believe what it is saying, it will always be true because people will do what the tool says. Yeah, one needs to think a bit about this. Yeah, and finally, the last important question is what actually distinguishes us from potential artificial scientists. So one could say we have creativity, but if you look at some of those super fancy pictures that were drawn by Dali recently, that even won art competitions, we cannot say that computers are not creative anymore. We can say we are curious, but I just mentioned something before that researchers and computer scientists are now very much investigating this type of artificial curiosity. And we could also apply this to our questions. Finally, we could say, okay, scientists understand stuff, computers just a machine, but then you have to think about what does that even mean? What does it mean that you understand something? And if you think about it, and if you can say clearly what this means, you can also make a program that can emulate what you wrote down. So it could also be that you could find something like machine understanding at some point. So I think there's a lot of cool stuff that will happen in the next years. Thank you.